Welcome back. Today, or in this video, we'll be talking about limits and continuity. It seems like you've been calculating limits, but there hasn't necessarily been a purpose. And this would be our biggest purpose yet. Something that I think we've taken for granted, but we'll look to flesh out. So we have 4 different visual representations here regarding continuity. So let's just ensure that we're all on the same page. In our first function, right, we can see a nice, beautiful polynomial where we have a defined value at c. So we can say that here that f of x is continuous at x equals c. Now notice here, right, we do have a defined value at c, but we also have an undefined value at c, right? So the left-hand side we're defined from, right? We reach a definitive value. From the right-hand side, we approach an undefined value. So here we would say that f of x is discontinuous because the left-hand and right-hand side are not equal. And by what we mean by the left-hand and the right-hand side is that the limit from the left and the right-hand side are not equivalent. Okay. This one should be a gimme, but if not, that's totally okay. We have a constant function, regardless what value along the x-axis we select, the value along the y-axis, or this line y equals k will not change. So we can say f of x equals k is continuous as well. And started to run a little bit of room. Right, but this is supposed to model the line y equals x since the input matches the output. And we can also see that this is continuous as well. So we really like continuous polynomials. So let's create a definition of continuity that can assist us moving forward. Alright, so we're defining continuity. Since I circle it, I'm not going to rewrite it, considering I don't have much board space. But assume that f of x is defined on an open interval containing c. We then say that f is continuous at x equals c if, let's change up the colors, let's go green, if the limit as x approaches c of f of x is equal to f of c. So, a lot of symbols here. Let's flesh this out in English. So, the function output at the limit we're observing must be equivalent to the behavior of the function. If the limit does not exist, or if it exists, because that can happen, but is not equal to f of c, we say that f has a discontinuity at x equals c. Okay, so I'll let you get that into your notes. If the limit does not exist, or if it does exist but is not equal to the output, we say that f has a discontinuity at x equals c. Alright, I know you can easily click pause since I am virtual at this point in time, so spare me your moans and groans without erasing the board. To summarize those 5 lines of text, we can say continuity at a point x equals c requires more than the existence of a limit. Three conditions must hold. Condition 1. F of c must be defined. Condition 2. The limit as x approaches c of x of x, s of x, f of x must exist. And condition 3, they must be equal in order for us to say that this function is continuous. Now, we do have some unique circumstances that we're going to cover next. So, let's say we have some graphical representation like this. 5, 10 as our outputs. Let's say right, so we have a function left and right side are tending towards what we can see is 5, but the function is undefined at 5, and we have a defined value at 10, right? So in this instance, right, we have a limit as x approaches c of x, f of x exists. However, the limit as x approaches c of f of x does not equal f of c. So, right in blue, we say that f has a removable discontinuity at x equals c. And if we take our symbolic and we just write it out, the limit as x approaches not c, but 2 of f of x is equal to 5. How do I know it's 5? If I were Ant-Man or the Wasp and I'm walking along this function, I'm steadily approaching 5, and from the left-hand side as well. Okay, so when we have the left hand and the right-hand side equal to each other, the function or the limit at that particular value exists, but we can see right. So we say as a conclusion, removal discontinuity at x equals 2. Okay, so that's scenario 1. Scenario 2 is slightly different. Let's take a look. let's say we have something along the lines of this. Okay. So graphically, you should be able to look at this and obviously see we have defined and undefined value, but also take a look at it from the left hand and the right hand side. I'm not going to say anything just yet, but if we were to say the limit as x approaches 2 from the left of this function, and let's go ahead and define these values again to be 5 and 10. So from the left hand side, we're coming in on 5. We also know that the output for f of 2 is 5. However, from the right hand side, we can see that the behavior of the function is tending towards 10. So based on our definition of continuity, it would make more sense, since the output is equivalent to the left-hand limit, we would say that this function is left continuous at x equals 2. But things could get screwy, right? I could easily turn this around. If I simply remove this defined value, place it here, and make this an undefined value, now it becomes a right continuous function. But we could also have a situation where in this instance, regardless of whatever these outputs are, our defined value is here, yet the behavior of the function approaches undefined values. So in this instance, we would have a neither right or left continuous function. So let's jot down a definition, and then we'll pause our video here. So our definition is a function f of x is called a left continuous if the limit as x approaches c from the left of the function is equal to the function output. And I'm certain that your intuition can tell you that if the limit as x approaches c from the right of the function is equal to the output, we would call that right continuous. Take a 30-second timeout on the coach, and then we'll pick up. Now, before we wrap up our section on limits and continuity, we do have to make a point regarding infinite limits. So in the event that we do have an infinite limit, we can say that the function has an infinite discontinuity at x equals c if one or both of the one-sided limits is infinite. Okay. So if you're just tuning in, our previous video spoke about one-sided limits and jump and removable discontinuities. So what's the point? Why do we have to talk about the graphical numerical approach, infinite limits, one-sided limits, discontinuities? It's getting us to this idea. Let's call this basic laws continuity. And if you're a calculus veteran, I definitely think this is something you may have taken for granted along the way, but hopefully in the next 3 to 4 minutes it'll be solidified and you understand why you do what you do when you evaluate limits. But if we can say that f of x and g of x are continuous, then the following functions are also continuous x equals c. They are as follows. 1, the sum of those two functions remains continuous. The difference of those two functions remains continuous. The scalar multiple of those functions remains continuous. The product of those functions remains continuous. And the quotient, assuming our denominator does not equal 0 at whatever function value we are examining. Okay. So once again, what's the big deal? Patience, patience. We're almost there. If you think back to, I think it was the previous video or the video prior, right? We had a rational function. So these are basic laws of continuity for polynomial functions, but in the event that we do have a rational function, we let p of x and q of x be polynomials. If p of x is continuous on the real numbers, and then their quotient is also continuous on its domain. And if you've forgotten here from pre-calculus or maybe algebra 2, the domain is the set of x values that allow the function to operate. So once again, for all values of x equals c, such that q of c does not equal 0, which is what allows us to use that basic limit law for quotients by simply separating the numerator and denominator and substituting in appropriately. It's all predicated on the fact that your numerator function is continuous for real numbers, and assuming that whatever value of c you're looking at, it does not turn the denominator into a 0. So we got all of our ingredients in our stew, calculus stew, even though it's summertime. So maybe a nice ceviche. Which brings us to what we've been doing this entire time, and probably what many of you have been doing forever. But now you know what you know, which is the substitution method, which says that when f of x is continuous, the limit is equal to the function value. And to look at this in symbols, that means we can simply directly substitute this value of c into the function. Whatever its output is what the limit becomes. And if you need further A vernacular, aka substituting x equals c into f of x. So let's do a couple of examples, and then that'll be it for us today. So let's say we have the limit as x approaches pi over 3, apologies, of sine of x. If you know the sine function, sine oscillates and is thus continuous. Therefore, we can take this value and simply substitute it in, which yields root 3 over 2. If you're unaware of how we arrived at that value, consult your unit circle or my pre-cal magic trick show. Alright, so we'll leave that one up. And one more for good measure. Let's make this one a rational function. But based on that most recent theorem, if we take a look at this function, it's exponential. That means it is continuous, especially at that value, in addition to the denominator. So since x equals -1, since both functions are continuous at x equals -1, thumbs up, proceed. So we can substitute, read to the -1 with the square root of -1 plus 5. This becomes 1/3. This becomes the square root of 4, which is really 2, 1/3. Keep, change, flip. Damn mnemonic devices. And we arrive at an output of 1/6. So the limit as x approaches -1 of this rational function is the same as its output, which is 1/6. And that'll wrap it and bring it full circle for limits.